This here, of course, is not proof of atoms, but no one has come up with a better explanation for this Brownian motion than atomic theory. This here, ladies and gentlemen, is evidence itself for the existence of atoms. To confirm the existence of atoms, all you need for this is a microscope, preferably one that goes to 400x. But all you really need for this, if you have a basic microscope, is a glass slide and a cover slip, and you need some milk, preferably one that has at least 1% fat in it. All you gotta do is take a little drop of milk, put it right in the center of the slide, just like that. You don't need much at all. Take the slide and put it on your microscope. Use my other hand for this. Stick the slide into place, and then you're going to want to use your high power objectives. This is 100, and then with the 10 power, this is 1000 power. Lock it into place. Lower down the objective until it makes contact with the immersion oil. This is what Robert Brown saw in 1829. You'll see the little droplets of milk fat are bouncing around. He wasn't sure exactly what this was, and although he was using pollen grain, he actually saw virtually the same thing. If I zoom in, you'll notice the little drops of milk fat are very animated. Now, back then they didn't know what this was. Some people thought that maybe these are living organisms, kind of like what you would see in a pond sample. Some people thought that maybe it was a mirage, kind of like on a road on a hot day, causing maybe a little rippled appearance. But Albert Einstein, at the age of 26, in 1905, he was single-handedly able to demonstrate that this was actually atomic theory, visible with the eye. Albert Einstein said that atoms are vibrating, and the atoms are kind of bumping into these little bubbles. And you can see the bubbles kind of knocking around like this. It's kind of like if you were to go to a concert and there was a mosh pit. You would be knocked around as well, with everybody banging their heads and jumping around. This here, of course, is not proof of atoms. No one has come up with a better explanation for this Brownian motion than atomic theory. This here, ladies and gentlemen, is evidence itself for the existence of atoms. This here, of course, is not proof of atoms. This here, ladies and gentlemen, is evidence itself for the existence of atoms.
This here, of course, is not proof of atoms. This here, ladies and gentlemen, is evidence itself for the existence of atoms.
Good afternoon, and this is Mr. McGee. A common question I get asked by my students is, how do we know that atoms are real? Well, rather than just sit there and tell them stuff, I'd rather them see with their own eyes. And I want to show you that same evidence that a Swedish botanist named Robert Brown first saw in 1829, and that was used by Albert Einstein in 1905 to confirm the existence of atoms.
What's up, guys? John the Morgile here. We're going to do a video that covers yet another bit of scientism that is etched in cultural belief as proven facts, and really the basis for so much theory in terms of atoms and molecules, and how that was allegedly all proven by Einstein in the early 1900s because he was able to mathematically predict how little specks of pollen would dance across the surface of different liquids. Once you're familiar with the signatures of scientism, it becomes clear the methods that were used to concrete such absurd theories into the scientific record as proven fact. So basically what Einstein did in a number of ways, but specifically we're talking about the atomic theory being proven allegedly by Einstein, is he mathematically described what was happening with the very small particles within a liquid being observed. And because he was able to mathematically predict with this theory, the theory was thus proven by the mathematics. Sound familiar much? It seems that any wild claim and assertion, whether or not the assertion is actually demonstrable or verifiable or sufficiently falsifiable, if you can create complex mathematics that work around natural observations, then you can pretty much claim that anything has been proven or has mathematical experimentation or mathematical description to back it up. And that's very much the case of what Einstein has been famous for in a number of respects. So, for one example, Einstein apparently predicted that specific stars would probably change their apparent position in the sky during an eclipse. So whenever the sun is in front of a star, its apparent position is going to change due to what Einstein called gravitational lensing. Now, for some reason, Einstein was able to correlate the fact that stars do apparently change their position in the sky when behind the sun during an eclipse. He was able to correlate that as mathematical evidence and proof of gravitational lensing. The argument is that the light from the star behind the sun is going to curve around due to the sun's gravity. The problem I have with this prediction of Einstein's is that if he knew ahead of time that stars do indeed change positions during an eclipse, then he could use any excuse, whether it was gravitic or something else. And as long as the prediction came to fruition the way that he described, then it would appear to circumstantially support his theory. Another very similar manipulation of experimental evidence by Einstein came in the form of time dilation. And yet again, if Einstein knew ahead of time that traveling at high velocities at high altitudes would change the actual speed of time, change the speed of a clock, then he could have predicted that it was gravity or any other thing, fill in the blank, that was causing time dilation. And so long as the time dilation occurred, it appears to experimentally support his theory yet again. However, it does not actually prove that gravity causes time dilation, and it does not prove that Einstein's theories were correct. It does just, in my opinion, prove that Einstein was very clever about how he framed his theories with predictions that he already knew the outcome to, and framed those outcomes into his theories so that when the predictions came true, they appeared to lend credence to his arguments. However, it was just a telltale sign of him being rather clever. In a deceptive sort of sense, that is. So the problem that I have with Einstein's interpretation of the Brownian motion conundrum is that he's assuming there are tiny particles, atoms and molecules, in the water, and they are vibrating around and bouncing around off of the particles of pollen in order to make the pollen dance around under the microscope, as you've seen. Now, by observing how that bit of pollen behaves, he's able to ascribe mathematical values to these hypothetical particles. And by apparently very keen observation and ascribing mathematical values to those observations, he was able to accurately predict, allegedly, how these sort of little particles behave. Now, on the contrary, I would argue that any number of things could be causing these particles to behave as such, and other contemporaries of Einstein felt the same way, that it was merely the flow of energy and not necessarily particles in motion bouncing around off of each other at an atomic sort of level. Because anything that's at the atomic or molecular level is too small for us to image with any sort of microscopics. So atoms and molecules have never been imaged. They are merely theoretical. However, because science can ascribe mathematical values to hypothetical atoms and molecules, and the mathematics work, then they are thus allegedly proven in the minds of science. Or at least enough circumstantial evidence has been presented to convince scientists that atoms and molecules are indeed there, even though we can't see them.
This here, of course, is not proof of atoms. This here, ladies and gentlemen, is evidence itself for the existence of atoms.
This here, of course, is not proof of atoms. This here, ladies and gentlemen, is evidence itself for the existence of atoms.
Now, I do agree that just because you can't see something doesn't mean that it's not there, but I would also argue that just because we can see little particles dancing around in the, waters, as Einstein noticed, does not necessarily mean that it proves atoms. If you assume that there are atoms there and construct mathematics around that premise, just because the math checks out does not necessarily mean that your theory is correct. It just means that you are good with math and your observations were correct. And that applies to everything from astronomy to atomic theory. Just because your observations are correct and your math checks out does not necessarily mean that your theory is correct. I would not be surprised to learn that Einstein stole his work in terms of this specific thing, because he's notorious for that. He's been notorious for that in so many other senses, and this sort of observation in mathematics just seems above his league. But even if he was the brightest genius in the history of the world, that does not necessarily mean that he was necessarily obviously correct on everything that he postulated. Most of his alleged proofs, mathematical proofs, were based on thought experiment as opposed to any sort of real tangible experiment. And while his numbers may work, it doesn't necessarily mean that he was accurate in his overall theory.
What's up, everybody? Welcome back to my laboratory where safety is number one priority. And this experiment I'm gonna demonstrate Brownian motion. Let's check it out. So I got here hot and cold water, and I got here ink. I got it from the pen and mix it a little bit with water. First we're going to drop couple drops of ink in a cold water and then hot water. So just a small drop. Well, it was a little bit more than one drop. As you can see, everything kind of stays together and sinking slowly down into the glass, kind of slowly. Now let's try the same thing in a hot water. Just a small drop. I put 3 drops. Let's see what happens. As you can see in this glass, it's actually kind of sink down really fast, and as you can see, it actually dissolves before it's hitting the bottom of the glass. Why is that happening? Simply because water made of particles, and they always moving, and the harder particles are, the faster they move.
While I can certainly get on board with the notion that the water is made of particles, I'm not so easily convinced that those particles are necessarily atoms and molecules. Again, just because you can ascribe mathematical values to observations of tiny particles within the water, tiny particles which would be tens of thousands of times larger than the atoms and molecules which are allegedly pinging against the particles at some random intervals, which ultimately causes the things to go in random motion throughout the medium. And so while this may suggest that there are particles within the water that are behaving differently depending on heat, I still don't see how that necessarily correlates to them being atoms and molecules. And again, just because you assume that there are in fact atoms and molecules and construct mathematics around observations of how particles actually behave, then again, it doesn't necessarily prove that your theoretical particles are there. It's just expressed and described in that matrix using the mathematics of that matrix. But if you were to assume that the particles were of some other type and size and use mathematics to describe observations using that matrix, then you would get completely different mathematics that would potentially check out as well, so long as your observations were accurate and your math was right. Also, when you take this sort of definition of heat as lots of little particles in motion colliding against one another, it does go against the whole idea of the thermosphere being, well, basically in a vacuum, because the very definition of heat requires lots of little molecules bouncing off of one another in close proximity and high density, if you will. And when you take away the pressure from the system, like you have in the alleged thermosphere where the ISS resides, they say it's thousands of degrees Fahrenheit, but the particles are disparate and separated. So I just don't see how you can rectify that definition of heat with the thermosphere in a vacuum. Alright, so let's look at this publication from jstor.org. thermodynamics in Wilhelm Ostwald's physical chemistry. So Ostwald was someone who disagreed with Einstein's theories involving atoms and molecules, and he was more attuned with what Nikola Tesla was on about, which was more along the lines of energetics, as they call it. So I'm just going to touch on a couple items here. Introduction to this. Wilhelm Ostwald was a professor of physical chemistry at the University of Leipzig from 1887 to 1905. He was awarded the Nobel Prize in Chemistry in 1909 for his work on catalysis and rates of chemical reaction. Ostwald sought to use parts of thermodynamics as a basis for an allegedly more general science of energetics. He accepted the first law as the law of the conservation of energy. He did not, to this author's knowledge, ever refer, and the author was Robert J. Delteet. He did not, to his knowledge, ever refer to the third law, and would not have accepted it in the now standard entropic form. Indeed, he minimized the importance of entropy in his formulation of energetic theory, and until later, the significance of irreversibility. I will therefore focus on the second law of thermodynamics. Section 2 offers a sketch of Ostwald's energetic theory. Okay, Ostwald once put it, he dared to, quote, construct a worldview exclusively from energetic material without using the concept of matter, end quote. The main features of that worldview are as follows. Every object or system is constituted of energy of different, distinct forms. Each form of energy, in turn, is resolvable into two factors, one indicating the intensity of the energy, and the other its capacity. Since such factorization is a, quote, universal characteristic of energy, end quote, Ostwald, like Helm, proposed a, quote, factorization principle, calling it the, quote, foundation of modern energetics. In Ostwald's version, this principle took the form where, in this equation, where E represents some form of energy, I is the magnitude of its intensity, and C is the capacity factor. Ostwald recognized a number of distinct forms of energy, two of which deserve mention. First, he admitted, indeed emphasized, the importance of volume energy as one of the spatial forms of mechanical energy and factored it as this equation here, where P is pressure and V is volume. He also recognized heat energy as a distinct form of energy. Initially, he factored it as Q equals T times S, where T represents temperature and S specific heat. Later, he factored it as Q equals T times C, where C stands for either heat capacity or entropy. An important consequence of this factorization is that entropy has an official role in Ostwald's energetic theory only as the capacity factor of heat energy for isothermal changes. Ignoring criticism that neither form of energy is a function of the state of the system, Ostwald insisted that every system has a definite amount of volume energy as part of its makeup, and that all but purely mechanical systems have definite amounts of heat as well. The total energy composition of an object or a system, in turn, is given by this equation here, where the sum extends over every form of energy present and n is greater than 1. To understand change, Ostwald directed his attention to the intensity factor of energy, quote, that property upon which the motion or rest of energy, that is, everything which occurs, depends, end quote. Energetic intensities are inherent tendencies of energy forms toward equilibration. Specifically, they are tendencies to pass over to regions of lower intensity or to be transformed into other energies, unless prevented from doing so. following Helm, Ostwald called this, quote, essential and universal fact about the behavior of energy the intensity law. So this goes on and continues, but more or less, Ostwald and several others broke away from Einstein's line of thinking in terms of atomic theory. However, this whole Browning effect that we looked at the beginning of the video somehow convinced all of science to go the way that Einstein decided he wanted them to go, which was chalking this circumstantial evidence backed up by hypothetical mathematics as absolute 100% proof in Einstein's theory of atoms and molecules.
These are the grains of bronze, and this is the polystyrene blob. And if I put this into oscillation, it jiggles about. And if I put the grain on the top, it goes in a random motion, a jittery motion, and moves to the side. If I do it again, put it in the middle, I can't get it exactly in the middle, so it's not exactly the same, and now maybe it'll go another way. And it does. And each time you do it, you might get a completely different path. Down at the very small level, are you focusing in on this, Brady? At a very small level, there are little grains coming in. If I pick one up, I can't, and it baffs into the side, then this will jitter that way. Another one will come and jitter it and ping it that way. So it's as though you're on a billiard table and all these balls are whizzing around in all sorts of directions. You put a balloon in the middle and these balls are bashing around in all sorts of directions, and sometimes it's kicked one way, sometimes it's kicked another way. So this is the idea that there are little molecules in here, in the water, that are acting in this way, and some of them are hitting one side of the balloon and other times are hitting the other side. And that's causing this jittery motion, which is why Robert Brown thought that this thing was alive. So you do this lots and lots of times, and you'll suddenly get the view that you can work out what's going on using Newton's laws of motion. And that's what Einstein did. He worked out from this that you could measure the diffusion of this pollen grain on the surface and measure the diffusion constant. But there's something else. If this is moving through this liquid, against all these pollen grains which are moving, there's a frictional force as well. And if you measured that frictional force of a grain moving in a fluid, which is known from Stokes' formula, you could work out this frictional force as well. And from the two, you could measure the kinetic energy of the particle. So what you're getting in effect is the kinetic energy, which is the amount of agitation it has, and you can relate that to the temperature of this liquid, the absolute temperature. And that's what Einstein discovered, that you could combine Newtonian mechanics with this random force to thermodynamics with gases and liquids having a temperature, an absolute temperature. And this connection he predicted, and Perrin went away, or I think it's Perrin, went away and did the experiments and measured all of this and proved it was correct, for which Perrin got the Nobel Prize. Einstein did.
One thing that's astounding about Einstein's publications in 1905 is that they spanned such a large range of physics. After illuminating the quantum nature of light by explaining the photoelectric effect in March, April saw Einstein turn to something apparently more mundane: particles suspended in fluids. In particular, if you look at tiny particles in water, or dust motes in the air, you'll see that they jitter about in a very odd and random way. That is, it appears odd and random unless you believe that the air or water itself is made up of even smaller particles called atoms or molecules, which just bounce off of each other according to very simple rules. This is called Brownian motion, despite the fact that botanist Brown wasn't the first to discover it, and similarly Einstein wasn't the first to describe it mathematically. But he did draw the conclusion that the mathematical description of Brownian motion is evidence for the existence of atoms, even if you can't see them directly. And then he cleverly derived how big atoms should be based on how much the Brownian particles move. That's like measuring the size of a penguin just by looking at how icebergs jiggle. Talk about cold and calculating.
Right, but these so-called Browning particles are going to move some measurable, observable distance. And as long as you document these measured motions of these so-called Browning particles, then you could assume that practically any size particles are hitting it and ascribe mathematics to that assumption. And as long as your mathematics accurately describe what is observed using the assumption correctly and the mathematics correctly, then the math will check out. But that doesn't prove that your assumption is correct. It merely proves that your math is adequate to describe observable mechanics of the situation under a given assumption of the size of the particles that are pelting this Browning particle. So hopefully my position on this argument makes sense, that I'll say it again, just because your math checks out doesn't necessarily mean that it's right. So hopefully at least that has been made clear. I'm going to go ahead and wrap this one up, and I think that further research is definitely warranted into atomic and molecular theory. First of all, we know that atomic bombs are definitely malarkey, and it appears that potentially even the entirety of atomic theory may very well be malarkey. When you've got things as ridiculous as this, little bits of pollen moving around in liquids, therefore there are molecules in there because Albert Schilstein was able to create complex mathematics around his observations, and he assumed that little molecules were bouncing around in the liquid, and since his math checked out, therefore there are necessarily atoms and molecules in there. So whatever. God bless you guys. Take it easy. As always, spread the word, spread the world, and peace out, everybody.